Welcome. In part 2 of chapter 7, we will continue our discussion of acids and bases. An anhydride is a molecule that is missing a water group to form another molecule. Anhydride itself means without water. There are examples of both acids and bases that have anhydrides. For example, nonmetal oxides are acidic anhydrides, and these can react with water to form acids. So any molecule that's an acid anhydride is a molecule that can react with water to form an acid, and any molecule that is a basic anhydride can react with water to form a base. Sulfur trioxide, for example, can react with water to form sulfuric acid. If you do a count on all the atoms at the start of the reaction, we end up with the same number of each atom at the end of the reaction. Metal oxides are examples of basic anhydrides. An example of a basic anhydride would be any molecule that can react with water to form a base. Lime, for example, is a basic anhydride, calcium oxide, that can react with water to form slacked lime or calcium hydroxide. The oxygen ion from the calcium oxide forms a new bond with one of the protons on water. After this acid-base reaction occurs, or the proton from water is transferred to the oxygen, we have two OH- ions, which can each facilitate one of the positive charges on the calcium. A strong acid and a weak acid are two different types of acids that can exist. A strong acid is going to completely ionize in water solutions. For example, we have HCl, or hydrochloric acid. This is an example of a strong acid. When we add HCl to water, every single atom of HCl turns into an atom of H plus and Cl minus. None of the molecule exists as HCl. A weak acid is only going to partially ionize in the water solution. For example, if we have hydrocyanic acid, some of the molecule will exist as HCN bound together, and some of it will exist as the ion pair of H plus and Cn minus. This same pattern exists for bases. Strong bases are going to completely ionize in water, and weak bases will only partially ionize in water solution. Sodium hydroxide is an example of a strong base, and when you put a sodium hydroxide pellet into water, it'll completely form the sodium ion and the hydroxide ion. Ammonia will be an example of a weak base. Ammonia will only partially ionize in the water solution. When the ammonia enters the water solution, some of the ammonia will accept a proton from water to form a basic solution. The NH3 begins to interact with the water, and one proton from the water, which is acting as an acid, creates a new bond with the lone pair on the NH3. This forms a positive NH4 plus ion and a negative OH minus ion and a basic solution. When an acid reacts with a base, a neutralization reaction occurs. This is going to be a reaction that results in the formation of a water molecule between the hydrogen ion and the hydroxide ion. We could see the H plus, which comes from the acid, can react with the OH minus, which comes from the base, and this forms a molecule of H2O. During this neutralization reaction, an acid reacts with the base to form water, but also a salt can be formed. Here is an example of a neutralization reaction between sodium hydroxide and hydrochloric acid. The sodium hydroxide is going to act as the base for this reaction, and the hydrochloric acid will act as the acid. When these two react together, the OH minus from the base reacts with the H plus from the acid to form a molecule of water. What's left over from this reaction that hasn't been incorporated into the water? Well, from the base, there's one atom of sodium, and from the acid, there's one atom of Cl. Therefore, the other product of this reaction is going to be the salt sodium chloride. All around us, different substances are going to have different levels of acidity or basicity. In order for us to be able to accurately and easily discuss how acidic or basic an item is, we use the pH scale. This is a scale that expresses the acidity or basicity of a solution. And the scale ranges from 0, being the most acidic, 7 being neutral, to 14 being the most basic. All substances will exist somewhere between 0 and 14 of a pH. We could see, for example, water, which is neutral, has a pH of 7. Oranges and tomatoes, which are slightly acidic, have a pH that range from 3.5 to 4.5. And sodium hydroxide, which we know is a strong base, has a pH that is all the way up at 14. pH actually means the power of hydrogen ion, or, in a mathematical term, the negative log of the concentration of hydrogen in the solution. Since the concentration of hydrogen can have an extremely large range of values, we could see we can have a concentration of 0 of hydrogen all the way up to a concentration of 1 times 10 to the negative 14th of hydrogen. Since this range is so long, it's much easier to visualize the data using a logarithmic scale, looking at values between 0 and 14. Here's a table that shows the pH of some household items and common solutions. Around 7 is pure water. This is going to be our neutral area. Anything close to 7, whether it's slightly acidic or slightly basic, is going to be considered a weak acid or a weak base. The closer our acids get to 0 and our bases get to 14, the closer they get to becoming a strong acid or strong base. When we have a pair of compounds that differ only by one proton, these are considered to be conjugate acid-base pairs. The only difference between these two molecules is that one proton that's being passed back and forth. For example, a conjugate acid-base pair would be hydrochloric acid, HCl. That would be the acid, and then the conjugate base would be Cl-, or the HCl after it's lost one proton. The only difference between these two molecules here is that the Cl- doesn't have a proton, which the HCl does. A buffer solution is a solution that contains a weak acid and its conjugate base. These solutions are extremely important in nature because they allow for a system to maintain nearly a constant pH when acid or base is added to the system. And that's because the conjugate acid-base system, the buffer, is able to accept a proton or give away a proton if additional acid or base is added. An example of a couple conjugate acid-base systems that are buffer solutions would be NH3 and NH4+, as well as hydrogen cyanide and sodium cyanide. These molecules differ only by one proton. Remember when we discussed acid anhydrides? These are molecules that can react with water to form acids. Acid rain is prepared by some of these acid anhydrides that are entering into the atmosphere reacting with water in the atmosphere. For example, carbon dioxide, sulfur dioxide, nitrogen monoxide, and nitrogen dioxide are major nonmetal oxides that are also acid anhydrides. And these molecules are responsible for acid rain formation because as they enter the atmosphere, they can react with the water molecules and form carbonic acid, sulfuric acid, and nitric acid in the atmosphere. When we look at the chemistry of the air, we'll look at these reactions in a little bit more details. Our stomach has a buffer system to maintain a fairly acidic pH. This acid allows us to help process and digest our food. In some cases, hyperacidity occurs when the stomach secretes too much acid, and antacids can be taken to neutralize this excess acid and the symptoms of hyperacidity. In some cases, if too many antacids are used, they can lead to an increase in the pH of blood and a condition known as alkalosis, which can be quite deadly. Here are some examples of common antacids that you might be aware of. These are basically just bases. We can compare the brand name of these antacids to the substance and formula. For example, Tums, which are quite common antacids taken for heartburn, is the molecule calcium carbonate with the formula CaCO3. In industry, acids and bases are used quite readily for many different processes. For example, sulfuric acid is one of the leading chemical substances produced in the United States, and it's used to manufacture fertilizers. It's also the acid that can be found in batteries. Production is about 40 billion kilograms per year of this substance. Hydrochloric acid has a number of uses as well, including rust remover, as well as a variety of different chemistry uses and household uses. It's used as a cleaner for plumbing as well as glassware. You can purchase it at hardware stores, and our annual production in the United States is about 4 billion kilograms. These are the two most commonly used acids, hydrochloric acid and sulfuric acid. Lime is produced by heating limestone and decomposing into calcium oxide and carbon dioxide. That calcium oxide is then a basic anhydride and can be used for a variety of different reasons that require base. One of the most common uses of slacked lime is added as a sweetener to fertilizers. This helps to ionize in the soil to produce OH- ions. Remember we discussed earlier how some rain can be acidic? Well, by adding the slacked lime to the soil, neutralization reactions will occur when this acid rain comes into contact with the soil. Sodium hydroxide, also known as lye, can be purchased as oven cleaners or drain cleaners. If you've ever used Drano, this is just going to be a concentrated solution of sodium hydroxide as well as some other molecules that create a gelatin-like substance. And this is used for cleaning pipes. It has an annual production of 9 billion kilogram, and it's also the most commonly used base in a chemistry lab, sodium hydroxide. It's a strong base. The other commonly used base is ammonia. Ammonia's production is vastly used as a fertilizer. So anywhere where you see a large amount of crops or farms, huge amounts of ammonia are being used. And this ammonia can actually build up in the environment, which is something that we'll talk about in the water and air chapter, and lead to some negative downstream effects. But our production of ammonia is about 11 billion kilograms per year.